Dry eye disease is a chronic condition that affects nearly 16 million people living in the US today. It can be directly linked to, but not exclusive to, a high screen time. This condition occurs when tears do not provide adequate lubrication to the eyes and can cause a stinging, itchy, and burning sensation, alongside eye pain and redness, blurred vision, and eye fatigue. Our goal was to design a test strip for a dry eye disease diagnostic device that could safely interact with the patient's eye while collecting the necessary fluid for biosensing. To do this, we developed a soft tip to maximize user comfort and biocompatibility, a microfluidic collection channel to draw the tear fluid to the sensors, and a product identification method so that each strip's information could be read by the sponsor company. These parts all came together to create a single-use test strip that can be manufactured at a low cost. The soft tip was developed with a focus on minimizing the distance the tear fluid had to travel to get to the collection channel. Starting with ideation, we discussed soft tip dimensions, shape, material, and opening design, then created a preliminary drawing. We developed a SolidWorks model and 3D resin printed the prototype using our material of choice, a biocompatible elastic resin. Each prototype was evaluated for fluid delivery, shape, size, and then the process was repeated to develop further iterations. Our final soft tip prototype uses a triangular shape to prevent sealing at the fluid interface and to make up the tip less intimidating to patients. The channel design started with research on microfluidics and capillary action. We chose a method to create the channel and then tested different materials for possible substrates, channels, and adhesives. We moved to physical testing of the channel itself, where we ran multiple iterations with varying lengths from 10 to 50 millimeters. The final channel design can hold over 2.5 microliters of fluid, which is beyond sufficient for biosensing. We chose to develop a QR code as a low-cost and accessible product ID method. This code needed to store each individual's test strip information to ensure data safety, privacy, and accuracy of the readings. This information is stored in a database, which we coded in SQL. It can contain up to 250 bytes of data and includes the company's ID, the product's lot and ID, and expiration. This database is linked to a QR code, which we developed using Python, so each strip will include a unique identifier that contains all of the necessary information. The QR codes can be printed or etched onto the test strip during manufacturing to be read by the device. The final step in our project was to integrate the three parts together into one test strip. With careful alignment of the collection channel to the soft tip and an engraved QR code on the outside of the channel, we were able to easily combine the pieces into a complete and effective biosensor collection tip for holding tear fluid and performing data analysis. When integrated into the biosensor, this test strip will include sensors within the substrate layer. The QR code will be directly printed onto the material, and a USB connector will be available to plug the strip into the handheld device. The database will be locally stored, and the QR code will be encrypted and automated to allow for secure, up-to-date testing information. In the future, this device may be expanded to diagnose conditions such as Parkinson's, Alzheimer's, and several types of cancer.